So thank you very much, everyone, for coming to this session. My name is Samir, and today me and my colleague from Line Corporation Japan, Nishiwaki-san, will present our neutron network solution that we find to be excitingly simple, and at the same time very robust when handling our own network workloads that we have in Line. So we hope that you'll find this presentation interesting and useful as well as we do. A little bit about Line. We are a communication and messaging platform #1 in our part of Asia. That's Japan, Taiwan, Thailand, some other countries as well. We have 200 million plus users for our application. On today's menu, first I'll explain a little bit about our main motivation for this approach that we took. Second, I'll provide some explanation of how we had achieved full network redundancy in our network fabric, all the way down to hypervisor level. That's the most important topic of today's talk. Next, I'll present why we had decided to adopt L3 routing instead of L2 in our overlays and our hypervisors. And from that on, we'll follow step with Nishiwaki-san. We'll dive deeper into the solution. What did we do in Neutron to achieve this? And he will also give summary of all the work that's been done here and providing some hints about future work. And finally, we will welcome your questions and comments. So let us begin. First, I'll explain our main motivation behind this work. So in Line, we operate massive scale messaging service, as long as some other services. And a fair number of these services are running on top of our private clouds, where the scale is growing and rapidly. Initial instances of our clouds used traditional data center network architecture. At the time, we had to use shared provider VLAN networks, and which are terminated on aggregation switches that we have on all layers shared between typical vendor L2 redundancy technologies like MC-lag, ECMP, etc. So this architecture worked fine for our cloud until we had to deal with scaling issues. As soon as we started facing traffic blocking limitations for these L2 solutions, we had to consider some other solutions. In traditional data center architecture, impose kind of limitation. Maybe some of you who operate these kind of networks had like problems like L2 storms, or maybe you had problems with bandwidth transgressing these entry points for L2 networks, etc. So we also face this kind of issues. Another issues that we faced is that our L2 zones, transversing traffic between L2 zones imposed some kind of traffic bandwidth limitations. And in the worst case scenarios, we had up to 42% loss of bandwidth between the TOR zones. And sometimes our traffic decreased to just 8% of the wire capacity, transgressing this east-west traffic, transgressing aggregation layer switches. So to picture this, after all clouds reached certain scale, we reached the point that we have much intense east-west traffic. So we had to start utilizing careful VM scheduling to work around these issues. We had to place traffic-intensive virtual machines under same TOR zones, and we also had to bring some sensitive service, same service, latency-sensitive VMs under same aggregation switches and aggregation zones. So to achieve this optimization and workarounds, we had to have a certain imposed scheduling where we had to use Nova aggregate zones to implement custom Nova placement hacks. Our production cloud was released in Mitaka era, so at that time, Nova placement API wasn't available. In our initial solution, each rack is actually an aggregate zone, and or our switch aggregate groups, we also have another layer of aggregation. So we had to hack Nova to replace our user-visible neutral networks with networks that are defined per Nova aggregate zones. It's a very ugly hack, but we had to have it in our production clouds. As soon as we started to significantly scale, many of these customizations and hacks and workarounds we took started to show imperfections. So we started to receive many pain points. And just to mention a few, this solution was hard to scale in terms of adding new hypervisors. So every time you add a new hypervisor, you have to customize the aggregation zones. You have to carefully plan this deployments, and these were pretty hard to automate and also error-prone. We also had impact on traffic bandwidth between TOR zones and aggregation zones, as I said before. We also had to enforce very annoying scheduling policies on top of users. Users don't really care about these details, but still they had to think about how to schedule their VMs. Finally, our initial cloud solutions required ugly hacks in Nova, and this is heavy customized hacks and code, which is very hard to maintain and delays upgrades, as you may probably expect. Also, I would like to say a little bit more about L2 provider networks that we used initially. So many of you may be aware of these limitations of these kind of networks. Normally, we need some sort of network node to handle these things, even though it's not a traditional network node in Neutron sense. It's a network node that needs to support some layer 2 functions like DHCP or metadata proxying, etc. So in large scale and huge scale networks that we had to run in our clouds, this is always a scalability point of failure. The more VMs you have on a single L2 network domain, the more chance there is you to have problems. So we found the hard way that L2 separation is really necessary, and but what did we do to achieve this? Now we're going to talk about this. Perhaps a small scale overlay typical for a small like tenants in a public cloud. This kind of L2 domains are pretty appropriate, but on our scale, where we have to communicate with a large number of VMs, this is not really appropriate. So for us, it's also perfectly fine if our VM only has L3 connectivity. So we had to consider how not to introduce points of failure by going back to L3 only, but still try to make this fully redundant and on both hypervisor layer, VM to hypervisor layer, as well as the network fabric layer. Also, our use case is perfectly aligned with provider LT networks, so we don't need tenant networks in our workloads. So for us, it's perfectly fine if we give user access to multiple provider networks with non-overlapping IP addresses. Thankfully, our network engineering teams were aware of these issues, and we talked together, and they were listening. And our initial network infrastructure limitations had to be fixed. So we all realized that, and we tried to build a robust solution that scales with our clouds as well. So together with these network engineers, we came with a new data center network fabric. So for most of our recent OpenStack-based cloud deployments and instances, we came up with one new network architecture in one of the new regions in our data centers. So this new architecture is inspired by CLOS BGP network, which totally abandons any featured L2 solutions. And basically, in CLOS network, we have balanced number of uplinks and downlinks, which doesn't introduce any blocking in the network bandwidth, etc. This is a well-adopted solution in big companies. So if you want to dive deeper into this approach, you can check RFC 7938, which is not really a standard. It's more like a recommendation on how to do large-scale networks in data centers. So we follow these recommendations, but we also had to integrate this solution with OpenStack. Introducing new network underlay architecture helped our cloud use case very significantly. So not only we got rid of traffic bottlenecks, but we also, it allowed us to get rid of ugly workarounds that we had before, and we also don't need to impose any ugly scheduling, unnecessary scheduling on the users because of this solution. Before we had to push this change, we strongly determined that our services don't really need any L2 networks. So on VM layer, on VM level, we don't need any L2. Seriously, we don't. So this CLOS architecture proven to be very suitable for our work case. Maybe some of you will find this work use case interested, maybe not, but it really depends on what do you run in your data centers. So I explained before how we use CLOS and BGP architecture, but what does it have to do with OpenStack? So for now on, I try to share a little bit more details about that. As we mentioned earlier, we choose BGP for DC redundancy as well as scalability, because that's the most important stuff for us. But we also choose this because we don't want to be vendor locked in any way. This solution also doesn't rely on any kind of vendor-specific quirks or solutions that might work only in single vendor and not across between the vendors. So I'm not going to spend more time praising this solution. Just check that RFC if you're really interested. So all of this is cool, but where is the OpenStack in this picture? How about Nova hypervisors and Neutron itself? How does it fit into this? Perhaps using MC lag on a hypervisor level is well understood approach in Neutron and OpenStack, but this solution that we have, we had to do some modifications in Neutron to really come to terms. We choose not to take any L2 approaches. We choose not to take like Linux bridge approach or any traffic capsulization kind of approach. We just try to go as much as possible close to this CLOS architecture proposed by RFC. So since now we have very nice and fully redundant L3 fabric, how do we integrate it with OpenStack in the most holistic manner, all the way from top of the rack switches to hypervisors and finally to VMs. Once we had introduced BGP between TOR and hypervisors, we got rid of all vendor-specific solutions, as I said. We also enable use of white box switches. Most of the stuff we run in this new cloud region is Cumulus-based. But we also have some, took some approaches very specific to our use case. We also decided that between TOR and the hypervisors, we could use the same way of BGP routing. So we achieved BGP L3 data center network enlightenment all the way to hypervisor level in our data centers. But what kind of choices did we have to make when decided about how to do the traffic between the actual hypervisor and the VM? That's something that we will dive deeper in. So at the point when we decide how the traffic is going between the hypervisor and the VM itself, there are some well-established approaches. So we were thinking about whether we use VXLANs or VLANs, or we do some kind of overlay approach. So, but since we already have benefits of having full redundant network in Fabric, in TOR to hypervisors, we also considered routing directly between VMs and the hypervisor. So overlay was one option, but we considered that, we tested it, and we find out that the actual, for our work case, for our workloads, simple routing might be more appropriate. In case of overlay approach, the overlay always introduce some kind of layer of complexities. Of course, it's an overlay. You have to have a meditation point between underlays and overlays. So many solutions would require some kind of dedicated network node, whether it's an actual traditional network node in Linux Bridge or VXLANs, but even in some more advanced so-called distributed network SDN solutions, there's always a network node, even if it's distributed together with hypervisors or if it requires some special distributed data store, etc. It always requires certain type of overhead. On the other hand, the simple neutron solutions like Linux Bridge or VXLAN always introduce agents that don't really fit into our scaling requirements. So we need something that is as simple as VXLAN, but also much more scalable and robust. After careful considerations, so we decided that simple static routing on a hypervisor between VMs and the hypervisor itself fits our needs the best. It doesn't introduce any significant performance overhead other than actual software layer 3 routing. But in its limited scope, in routing just between VMs and the hypervisors that always goes one way upstream, that's pretty low overhead. Also, we had to have certain kind of agent that manage all these routings and all these bits necessary for VMs to actually have a full life cycle. So our agent is very, very light, low footprint agent that runs on each hypervisor. It's a fairly distributed architecture. So to summarize, we decided to ditch L2 and just use L3 on VMs as well, all the way from VMs to the core switches. We had to do some tricks to make VMs be able to join, to boot, to provision their networks and metadata. So Nishiwaki-san will tell you a lot more about the implementation details and how we achieved some kind of fake L2 functionality for VMs, but we also kept L3 all the way in our network fabric. So Nishiwaki-san.
So up to here, we explained about why did we use cross-network and why did we need the custom plugin. From here, we are moving closer to OpenStack side and talk more details about custom plugin. We call our custom neutron plugin as L2 isolate plugin. This plugin provides new type of network. Under new type of network, none of end devices share L2 network at all, but ensure all end devices to have L2 connectivity between VMs. So how did we achieve this? Basically, the hypervisor maintains the routing table for every VM's IP running on same hypervisor and does L3 forwarding. And also, the hypervisor propagates the VM's IP to the peering routing software running on the TOR switch to provide the access to VMs from outside of hypervisor as well. This is the basic idea for our solution. In order to achieve this, we need to configure the hypervisor according to the VM's network state change. And our L2 isolate agent has that responsibility to do all necessary configuration. For example, once VM is created on the hypervisor, this L2 isolate agent configures the proxy app for that top device and inject the static route for the VMs and propagate the VM's IP to the peering router, and then update port status in Neutron database. This is the overview of L2 isolate agent implementation. I will provide more details on later slide. So from the operator point of view, our agent does not just change the actual service daemon from Linux Bridge agent to the L2 isolate agent. This agent does also change how OpenStack networking services are deployed. Above part of diagrams show the OpenStack deployment with Linux Bridge agent with 3 types of nodes: controller, network, and compute node. On the other hand, shown below is that OpenStack deployment with the L2 isolate plugin. You might notice some difference between them. The obvious change is that we are using the mechanism driver and type driver for our custom implementation. And also, we got rid of the network node from our deployment. And also, we moved the metadata agent from network node to the compute node. And then about the DHCP agent, DHCP agent have disappeared from this deployment completely. And now the DHCP service is provided by the L2 isolate agent running on each compute node. This change was needed because with L2 isolate environment, the Nova compute node provide the DHCP service to the all VMs on a local hypervisor, because computer node terminate L2 network, but VM need L2 connectivity to the metadata proxy and DHCP service. That's why we have to relocate the metadata agent, and DHCP service is now provided by the L2 isolate agent. So moving on the internal L2 isolate plugin implementation. Neutron have many plugin entry points, and we can replace any of them with custom implementation thanks to plugin architecture. So we did replace green part with the L2 isolate plugin part. We did implement 3 parts. Type driver to represent new type of network, and mechanism driver to correspond to the custom agent, and custom L2 agent running on each compute node, and doing actual configuration and manage DHCP and metadata service. On our next slide, we can have a look at more details for each of 3 parts. Starting from the type driver, it doesn't have much business logic, and it only needed to represent the new type of network called as rooted type. The rooted type network is that network ensure no L2 network between the end devices, but ensure all end devices to have L2 connectivity. As for the mechanism driver, this one also does not have much business logic. This driver just supports the rooted type network I explained in the previous slide. And this mechanism driver uses the tap VIF type to let Nova create just simple tap device per instance. And does some additional validation like preventing IP address overlap. So I mentioned we use tap VIF type, but why? Actually, we got the question related to this choice very often. So let me clarify. So first question one may have is why do we need L2 isolation inside hypervisor when we could assume L2 network is already isolated between hypervisor by data center network design? We do this because even in private clouds, shared network is not always trusted, so we believe it's better to isolate L2 network if it's possible. And also, we wanted to make communication paths between VMs unified, not to use both L2 at certain paths, L3 at other paths, which we think is just unnecessary complexity to the operator and end user. And next question you might have is why not use just dedicated bridge to achieve L2 isolation inside hypervisor? This is because if we can achieve the objective with just simple tap device, we should not create any other extra resource. Extra resource is just unnecessary complexity. That's why we use tap device as VIF type. So moving on the agent part. Our custom agent is most important part in our custom plugin, having many business logic. So basically, it monitors all tap devices on a hypervisor and does some configuration once the tap devices has been created, updated, removed. This design is very similar to the Linux bridge. And also, this custom agent does support the IP tables-based security groups by introducing tap-based firewall driver. So let's deep dive into how the computer node is running L2 isolate agent. Imagine this as kind of snapshot of computer node running in our OpenStack cluster. And this is showing internal configuration that L2 isolate agent is doing. One can see in the 3 different colors. Yellow boxes indicates the existing OpenStack software stack. And the green boxes indicates the existing OpenStack software, but used in a different way. Maybe you may be familiar with. And the blue box represents our custom implementation. So let us look at these step by step. So started from the part explaining connectivity between VMs inside hypervisor, from left to right. Nova Compute creates just tap devices for the VMs. And the L2 isolated agent showing the right side detected that new tap device and configured the proxy for that tap device and configured the gateway IP with no prefix route option, preventing from injecting the prefix-based routing information. And the last thing is this L2 isolated agent injects the VM's IP/32 static route to the routing table so that hypervisor can do L3 forwarding between VMs. This logic enables the VM to access the other VMs inside the same hypervisor. So, but how about connectivity between VMs living on different hypervisor? Our all compute node run the routing software configured to watch the routing tables on the hypervisor. And once the routing table has been changed, this routing software detected that change and advertised and withdraws VM's IP according to that change. This logic advertises where the traffic intended for the VM can be sent so that the VM could be accessed from outside of hypervisor as well. Moving on DHCP part. Since hypervisor terminates L2 network, we need to provide something DHCP service to all VMs inside hypervisor. Usually, DNS mask is used to provide DHCP service in the general OpenStack deployment with DHCP agent. But with L2 isolate agent environment, we use this L2 isolate agent to provide the DHCP service as well. And this L2 isolate agent spoon the one DNS mask instance to provide all VMs inside hypervisor, regardless of the subnet VM belong to. And this DNS mask instance is configured to monitor two directories. One directory is for the configuration describing the MAC and IP address pairs, which is created for each port. And the other directory is for the configuration describing the DHCP option, like gateway IP or static routes, which is created for each subnet in Neutron. And once something configuration has been changed inside these directories, the DNS mask process automatically reloads and provides DHCP service to all VMs inside hypervisor. About metadata proxy, we do also reuse the single metadata proxy for all VMs on same hypervisor, regardless of how many subnets we have. In order to do this, we have to pass the fake router ID to the metadata proxy. And if we pass the fake router ID to metadata proxy, this metadata proxy forwards the metadata IP access for VMs to the metadata agent with fake router ID. And if we pass the fake router ID to the metadata agent will look up the instance ID by just VM's IP, not additional other information. But if we pass the valid router ID to the metadata proxy, this metadata agent tries to look up the VM's IP and the network belonging to that router ID. In doing this way, we are providing the metadata service to all VMs by the single one metadata proxy. The last part is the security group. The default IP tables firewall driver expected the tap devices to be connected by a bridge, but we are not using any bridge. So we had to change the condition to judge if the traffic is intended for the VM or not in the default firewall driver to just check by checking if incoming or outgoing traffic is associated with VM's type 1 node. Otherwise, the VM's traffic is not read through security group chain. So I finished explaining all of the configuration that L2 isolate agent is doing actually in order to make VM connected to the L3-based data center network. So perhaps now these diagrams make a little more sense to you. So a summary of this presentation. In our most recent OpenStack deployment, we were challenging to use cross-networking and use L2-less networking plugin we introduced today. We achieved 4 things by this challenge. First one is that the average throughput of VM to VM traffic over TOR is improved quite significantly by improving the uplink bandwidth of TOR and use no overlay solution. The second one is we got completely free from the L2 redundancy mechanisms, so we don't need to be worried about some vendor special things to achieve the L2 redundancy. And now our redundancy has been implemented by just one simple BGP protocol. So to operate our OpenStack environment and data center network, we need just BGP expert. The third thing is we don't need network nodes, thus avoiding the bottlenecks and point of failure. If you have any experience to operate with the shared network, you have some noisy neighbor issue against the networking service, but we don't need to be worried about it with this deployment. The last one is that the portable instance IP. So now we can do live migrate everywhere inside OpenStack cluster. Of course, our solution may be not perfect for everyone, and we are aware of some negative things. Now that BGP is everywhere in our data center, so we have to operate massive scaled BGP network, but it is much easier than operating massive L2 network and multiple network protocol. And we did develop custom plugin and started to use it in production already. So we have to maintain that custom implementation for long and taking care of some upgrading stuff. And in our OpenStack deployment, we cannot run any software depending on the multicast and broadcast. These are possible negative things, but we can compromise on them for the reason I stated in the previous slide. As today we talked about the challenge we faced and we solved, yet we are doing extra work to improve our solution. First we are thinking to do is to make this plugin OSS as a new neutron plugin. Next one is that we are trying to work on the L3 forwarding offload. Now that UR bottleneck has been gone, so next possible bottleneck will be the L3 forwarding software processing on each hypervisor. The last things would be the support overlay network as well as the routed type network. Our earlier workload doesn't require any network separation, but recently we got some requests needing the network separation for security reasons. So that's why we are thinking to support the overlay network as well as the routed type network. So how to coexisting these different network models in our OpenStack would be the next challenge. So this is all we prepared today. Thanks for listening to our presentation. So let us use the rest of time to open the question, if anyone have.
So I noticed you're not using namespaces. You're putting everything into the base routing table of hypervisors. Did you look at using namespaces? Or?
We intentionally avoid using namespaces because we don't need that kind of isolation. That's our use case. That's our requirement. In the future, we might consider using those things again if we really opt to use tenant network isolation as required.
This network model, it seems to be pretty much the very same as you would get when you use the Calico plugin from
Exactly.
Did you ever consider using that plugin and work together with them? Or if you did consider them and ditch them, why did you make your own?
So that's a good question. Actually, when we started working with this, when we had this kind of requirement known to us, Calico was pretty much in infancy stage. So we consider it even now, maybe we could switch it or maybe not, but it turned out this solution was much less costly for us. We developed the whole solution in less than 2 months, including the testing, including the integration testing, etc. We leveraged existing Neutron and Neutron-dependent open source software like DNS mask, etc. Just using it slightly different way, this was pretty much very, very effective way to do it. So, of course, this pulls the question of whether we are going to be able to maintain it or maybe upstream it. So we are considering it now. We think this solution is pretty much more appropriate for our use case and our workload than Calico. Calico has extra complexities when it comes to actual, well, it has to deal with certain container use cases we don't really need to deal with. But still, we will consider it again. Since we also have a container-based workloads that are other kind of problem we need to solve, we also consider Calico for this and maybe integrate with our own approach. Thank you.
Okay, thank you for your presentation. In your use case, would it be possible for the VMs to use multicast? And what about HA IP addresses with VRRP or CARP or whatever? Would it be possible to use?
Actually, we cannot use on this deployment. We cannot allow, no, we don't allow the user to run something software depending on the multicast broadcast.
Yeah, one of our slides explicitly mentioned we can't use multicast because most of the normal layer 3 multicast kind of depends on L2 functionalities, and we intentionally got rid of L2. Maybe some certain load balancing BGP-based multicast might be an option, but we have to consider that seriously in the future.
Thank you.
I built something really similar to that for Ceph, and one thing that we ran into, the Cumulus gear that you guys say you use as well, has a resource limit, and you start hitting it as soon as you have 5,000 routes.
Right.
So have you hit that, and how do you plan to work around it?
It's a good question. We are not directly involved into this part. We have other bunch of network engineers dealing with these problems, but they try to organize the layers of switching into multiple BGP zones to avoid this kind of problem.
Okay, so you're just going to avoid it
yes,
through aggregation.
For now.
And have less than 5,000 VMs in a single rack.
So, yes. Right now, we try not to have more than that. But we might even consider like one rack can, in theory, it could be 2 different BGP ASs or something like that.
The limit is per switch, so you
per
actually
switch.
Need a physical switch.
Yeah, physical switch. So I hope Cumulus comes something with some better solution than it exists now. I don't know if it's a hardware limitation or...
Yes, it is.
Well...
Maybe newer hardware.
Yeah. So if you talk about, is it a Broadcom limitation? Or
the 5,000 was on the Trident 2 series, and there's different limits on some of the other units.
Right. So that's why our engineers decided not to use Broadcom.
Okay. So I see like your computes are dual connected, right? I mean, you have 2 ports on them. So how do you handle, provide one IP from a management perspective? I mean, if you're running BGP peering to the both sides of the switches. And I have another follow-up question.
So basically, a VM receives a /32 IP address on a hypervisor from whichever port the inbound traffic comes in, or the outbound traffic has to go out, it's just a matter of routing how to decide those ports. So we don't have to do any L2, I don't know, MLAG stuff to see which link is active, which one is not. The BGP agents on hypervisors will take care of that for us.
Second question is, so you rely on BGP timers, right, to withdraw the route. So it takes a while, right? I mean, you can set the timers really low, but
yes.
How do you handle that?
That's actually pretty well explained in RFC that we referenced to in one of the slides. So I think we just follow that recommendations given there. There are a couple of 2 or 3 workaround kind of solutions for these problems. I think one of them rely on combination of monitoring the link state as well as ability to route traffic from 2 different ports, something like that. I cannot give you specifics because me and Nishiwaki-san, we were concentrated on providing this solution on OpenStack layer and hypervisor layer. Between this BGP peers, that's not something we were really focused on. But if you check RFC, I think you'll find some answers to that.
Just a question around the layer 3 from host to top of rack switch. So I take it you guys are not doing any like EVPN overlays in the fabric itself. Okay, because if you do, the problem with that setup of having L3 from the host to the switch is that those L3 connected hosts cannot then talk to other hosts that are using EVPN overlays. We ran into that problem. Like the chipset has a limitation; it can't do like L3 and then do the in-cap or something.
Right.
So in that case, we had to actually move back to standard bonding, like lag for the host. We still did BGP on the host. We still did routing on the host, so that still worked out. But it's kind of a compromise, and you also get faster failover times.
Right.
With the bonding, actually.
Right. That's something like I think our network engineers came with this kind of weird solution for that. Like only do VMs would only use IPv4, but the BGP peers will only use IPv6. And the case we need v6 on a VM side, then just like swap these 2 things. But I'm not sure about it. We haven't really touched the BGP part on actual switches.
Okay. Are you using IP-connected storage for the VMs? Or
sorry?
Are you using like IP-connected storage like Ceph or something for the VMs? Or are you just using like local disks?
Both.
Okay, because that's another thing, is like the failover time on bonding is a lot quicker than BGP. So like the BGP, I think the best we could do was like a second or 2.
Yeah.
Which was, and it was like 3 seconds, which was like too much for the storage solution we were using. So.
Yeah, that's quite true. But again, in the RFC that we referred to, there are some advanced and much quicker way to combine the link monitoring as well with the and give that status to BGP agent so it knows how to switch faster. Thank you.
Thank you.
If you have any more questions, we can talk outside here in front of these doors. Thank you very much.